On October 22nd, 2025, in a nondescript lab in Santa Barbara, a machine smaller than a refrigerator did something that no computer built by human hands had ever done before. It didn't just calculate faster. It reached into a place classical computers physically cannot follow, the tangled, chaotic inner motion of a molecule, and pulled out an answer that would have taken one of the fastest supercomputers on Earth more than 3 years to even estimate. The machine did it in seconds. And unlike every quantum claim, before it, this one could be checked, verified, and repeated. For decades, artificial intelligence had been sold to us as the technology that would solve everything: cancer, climate, the mysteries of the human genome. But AI, no matter how large its neural network, was still built on classical bits, and some problems simply refused to bend to classical logic, no matter how much computing power or data you throw at them. This is the story of what happened when a different kind of machine finally showed up to those problems, and what it found. To understand why this moment matters, you have to understand the wall that both classical computing and artificial intelligence have been quietly running into for years. Every large language model, every AI drug discovery platform, every neural network trained to predict protein shapes or optimize a supply chain ultimately runs on transistors flipping between 0 and 1. That architecture is extraordinarily good at pattern recognition, language, and statistical prediction. But nature itself doesn't compute that way. Atoms, electrons, and molecules exist in superpositions, entangled states, and probability clouds that classical bits cannot represent without an exponential explosion of memory and time. Simulate a modestly sized molecule with 50 electrons in full quantum detail on a classical computer, and you're not looking at a few extra hours of processing. You're looking at needing more memory than there are atoms in the observable universe. This is not a limitation of AI's intelligence. It is a limitation of the hardware AI runs on. And it's precisely the gap that quantum computers are built to fill, not by being smarter, but by being built out of the same quantum stuff the problem itself is made of. That gap has a name in the industry: quantum advantage. It's a term that gets thrown around loosely in headlines, so it's worth being precise because for years the phrase was misused. Quantum advantage means a quantum computer has solved a specific, real problem faster, cheaper, or more accurately than any classical method available, and crucially, that the result can be independently verified. Back in 2019, Google's 53-qubit Sycamore processor made global headlines by claiming to perform in 200 seconds a calculation that would take the world's best classical supercomputer roughly 10,000 years. It was a landmark, but a shaky one. IBM quickly countered that with smarter classical techniques. Its own supercomputer could actually finish the same task in about 2.5 days, not 10 millennia. And the deeper problem was that the task itself, known as random circuit sampling, had no real-world use. It was a magic trick designed to prove quantum computers could outrun classical ones, not a task anyone actually needed solved. Physicists at the time openly admitted that while the demonstration was an important milestone, it did not represent a breakthrough with broad practical significance. That honest asterisk hung over the entire field for 6 years. What changed in October 2025 is that Google closed that asterisk for the first time. Google's quantum AI division unveiled a new algorithm called quantum echoes, run on its 105-qubit superconducting Willow processor, using a technique built around what physicists call out-of-time order correlators, or OTOCs. Think of it as a way of sending a signal into a system, letting it scramble and evolve chaotically, then reversing time on that evolution and listening for the echo that comes back. That echo carries hidden information about how a system's internal structure is arranged, information that is otherwise buried in noise. Using this method on a 65-qubit subsystem of the Willow chip, Google's team extracted structural data about molecules that would ordinarily require nuclear magnetic resonance experiments in a physical lab. Certain individual data points from that experiment were estimated to take over 3 years each to simulate on Frontier, one of the fastest classical supercomputers currently operating in the world. Willow produced the same signals in a matter of seconds, and the results were published in Nature and reported as running roughly 13,000 times faster than the best available classical estimate. The key word, the one that separates this from 2019's Sycamore moment, is verifiable. Because the OTOC signals can be cross-checked on other quantum devices of similar quality, this wasn't a black box calculation you simply had to trust. It was an experiment other scientists could actually confirm. It's worth sitting with what that 13,000 times figure actually represents, because on its own it's just a number, and numbers like that are easy to let wash over you. Imagine you're trying to read a book that's written in a script so dense that it takes a professional translator 3 years to decode a single paragraph. Now imagine a second translator walks in and reads that same paragraph aloud, correctly, in under 10 seconds. That's roughly the scale of what happened inside that Santa Barbara lab. And it wasn't a party trick. The specific thing Willow was reading was the internal architecture of a molecule, the kind of structural information pharmaceutical chemists rely on to understand how a drug candidate will actually behave inside the human body. Google's own researchers framed it plainly. This is a way of learning the structure of systems in nature, from molecules to magnets to black holes, and it represents a genuine step toward the technology's first real-world applications, not just another lab curiosity. This is where the AI couldn't part of the story gets its teeth. Artificial intelligence has had its own celebrated triumph in molecular science. AlphaFold, the DeepMind system that in 2020 and beyond cracked open the decades-old problem of predicting a protein's three-dimensional folded structure from its amino acid sequence. It was, rightly, treated as one of the great scientific achievements of the 21st century, and it has already reshaped structural biology. But AlphaFold's genius has a boundary. It predicts a static snapshot. The shape of protein settles into once it's done moving. What it cannot do, because no classical AI model can do it from first principles, is capture the quantum mechanical electronic structure and the constant, flickering motion of a protein as it interacts with a drug molecule in real time, the conformational dynamics and subtle structural shifts called allostery that determine whether a medicine actually binds correctly or not. That dynamic, electron-level behavior isn't a data problem that more training data can fix. It's a physics problem, rooted in quantum mechanics itself. And it's exactly the kind of problem quantum hardware is built to represent natively. That's not a hypothetical distinction anymore. In March 2026, IBM and the Cleveland Clinic published what they described as the world's first quantum classical hybrid simulation of the full electronic structure of a real, biologically relevant protein fragment, a 303-atom mini-protein called TRP-Cage, run on IBM's Quantum Heron R2 processor. This wasn't a toy molecule chosen because it was convenient for a qubit count. It was a genuine step into protein-scale quantum simulation, the exact terrain where AI's structural predictions run out of runway and quantum mechanics takes over. Around the same period, the French company Qubit Pharmaceuticals, working with the neutral atom quantum computer built by Pascal, demonstrated quantum algorithmic placement of water molecules inside protein-binding pockets, a molecular biology-grade task that directly affects how tightly a drug candidate binds to its target. These aren't demonstrations run for headlines. They're the first data points in what researchers are now calling the crossover point, the moment, where quantum simulation starts outperforming classical density functional theory on molecules complex enough to matter. As of early 2026, quantum hardware could accurately simulate molecules with around 20 active orbitals, which is roughly where classical methods already perform well, meaning the crossover hasn't fully arrived yet, but the gap that once looked unbridgeable is now measured in single-digit years, not decades. There's a second dimension to this story that's just as important as the molecular biology angle, and it has to do with the sheer scale of chemical space itself. Researchers estimate there are somewhere on the order of 10 to the 60th power possible drug-like small molecules, a number so large that if every atom in our solar system were a separate calculation, you still wouldn't come close to covering the space. Classical AI models, no matter how sophisticated, can only ever explore a vanishingly small slice of that space because they're fundamentally searching through it the way you'd search a maze. One path, or one batch of paths at a time. Quantum computers, because of the way superposition allows a system to represent many states simultaneously, offer a theoretical path to compressing that search exponentially rather than linearly. That's not yet a solved problem. The qubit counts and error rates needed to actually execute that kind of search at meaningful scale don't exist yet outside of small experimental demonstrations. But it reframes what AI couldn't actually means here. It's not that AI failed. It's that AI was never structurally capable of touching that part of the problem in the first place. The same way an incredibly skilled cartographer can't map a country by walking every single road in it one at a time. You need a fundamentally different tool, not a faster version of the old one. None of this happened in a vacuum, and it's worth understanding just how fast the surrounding race has been moving, because Google's October 2025 milestone was really the visible tip of an enormous, quietly accelerating engineering effort. IBM, Google's largest rival in this space, laid out a detailed roadmap in mid-2025 that reads almost like a modern-day space program. The company is currently rolling out a processor called Nighthawk, designed to run circuits with roughly 7,500 gates across up to 3 connected 120 qubit modules through 2026, scaling to 15,000 gates by 2028. Behind Nighthawk sits a processor called Loon, introduced in 2025 to test long-range qubit connections called C-couplers, which are essential for a new and more efficient error correction approach known as quantum low-density parity check codes, or QLDPC. In 2026, IBM plans to introduce Kookaburra, its first module capable of combining quantum memory with logic operations. Effectively, the basic building block needed to scale a fault-tolerant machine beyond a single chip. All of this is aimed at a system called Starling, planned for 2029 at a new IBM data center in Poughkeepsie, New York, which the company says will be capable of running 100 million quantum operations across 200 logical qubits, and which would require, to represent its full computational state classically, more memory than exists in a quintillion of the world's most powerful supercomputers combined. IBM's own executives have been unusually blunt about what this means. The company has said it now believes building a large, useful quantum computer is a question of engineering, not physics, a sentence that would have sounded absurdly premature just 5 years ago. Meanwhile, roughly 7,000 miles away in Hefei, China has been running its own extraordinarily fast-moving program, and by several measures, it is not behind at all. In December 2025, a team at the University of Science and Technology of China, led by physicist Pan Jianwei, alongside Zhu Xiaobo and Peng Chengji, announced that their superconducting processor, Zuchongji 3.2, had crossed a critical threshold in quantum error correction, the point at which adding more physical qubits to protect a logical qubit actually makes the system more stable rather than less. That might sound like a small technical footnote, but it is, in essence, the single hardest unsolved engineering problem in the entire field, the same threshold Google's Willow chip became famous for crossing back in December 2024. What makes China's version notable is the method. Rather than relying on the hardware-intensive suppression techniques Google uses, the Chinese team built what they call an all-microwave control architecture, which independent physicists outside the project, including Joseph Emerson at the University of Waterloo, have said could offer a more resource-efficient path to the same destination. China has also opened its 105-qubit Zuchongji 3.0 system to public commercial and research use through a cloud platform called Tianyan, which by early 2026 had logged more than 37 million visits from researchers in over 60 countries, turning what used to be a closed national lab experiment into a globally accessible research tool almost overnight. Then there's the wild card, the approach that half the physics community isn't even sure is real yet: Microsoft's bet on topological qubits. In February 2025, Microsoft unveiled a chip called Majorana 1, built around a theoretical particle-like state, first proposed by physicists Alexei Kitaev and Michael Friedman back in 1997, which in principle offers a kind of built-in physics-based error protection that superconducting qubits have to achieve through brute force redundancy instead. The claim was electrifying and immediately controversial, because the underlying quasi-particle, called a Majorana zero mode, is notoriously difficult to prove actually exists inside a device, rather than just mimicking the signal of one. In June 2026, at its Build Developer Conference, Microsoft doubled down, unveiling Majorana 2 and reporting a roughly 1,000-fold improvement in qubit stability, with topological qubit lifetimes stretching past 20 seconds, compared to the millisecond scale lifetimes typical of the previous generation. The company said the leap came from swapping aluminum for lead in its superconducting materials and widening what's called the topological gap, the physical property that shields the qubit from environmental noise. On the strength of that result, Microsoft accelerated its own roadmap, now targeting a scalable quantum computer by 2029 instead of 2033. But the skepticism hasn't gone away. Physicist Henry Legg of the University of St. Andrews said publicly that nothing in the new data resolves the field's fundamental objections. And physicist Sergei Frolov noted that the underlying research track record still isn't the kind of solid foundation extraordinary claims usually require. Even some sympathetic voices, like physicist Kartiek Agarwal at Argonne National Laboratory, who called the new measurement method fantastic progress, stopped short of declaring the debate settled. It's a useful reminder in the middle of all this momentum that not every quantum headline in 2026 has been fully verified, and that the field itself polices its own claims more rigorously than the press coverage around them usually suggests. So where does all of this actually leave the comparison the title of this story makes? Quantum computers solving what AI couldn't? The honest, unhyped answer is more interesting than a simple victory narrative, and frankly, more useful if you actually want to understand where this is heading. Quantum computers have not replaced artificial intelligence, and nothing happening in labs in Santa Barbara, Hefei, or Poughkeepsie suggests they're about to. What's actually happening is something closer to a division of labor becoming visible for the first time. AI remains extraordinarily good at pattern recognition across massive datasets, predicting a protein's likely folded shape, screening millions of existing compounds for promising candidates, or writing code and language at superhuman speed. What AI cannot do, no matter how many parameters you add or how much data you feed it, is directly simulate the quantum mechanical behavior of the molecules and materials those predictions ultimately depend on, because it's built on hardware that fundamentally doesn't speak that language. Quantum computers, even in their current noisy, error-prone early state, are starting to speak it. Google's Quantum Echoes results showed that a quantum processor can now pull out real structural information about how molecules actually move and organize themselves at the atomic level, verifiably, faster than any classical system, AI included, ever could. IBM and the Cleveland Clinic's work on the TRP cage mini protein showed that quantum hardware is beginning to reach past the boundary where AlphaFold's static predictions stop and the messy dynamic physics of real biological interaction begins. Neither of these breakthroughs makes AI obsolete. They fill in the exact piece AI was never built to hold. What makes 2026 feel different from the false dawns of the past isn't any single result. It's the accumulation of independent confirmations arriving from competing labs using completely different hardware approaches, all pointing the same direction at roughly the same time. Superconducting qubits at Google and IBM, an entirely different superconducting but microwave-based approach in China, and a completely different physical paradigm in Microsoft's topological bet, are all reporting crossing the below-threshold error correction milestone within about 12 months of each other. Peer-reviewed research output in quantum error correction alone more than tripled between 2024 and 2025, jumping from 36 papers to well over 120. Investment has followed accordingly, with billions of dollars flowing into fabrication facilities, national strategies, and specialized quantum pharma startups. The market for quantum applications in drug discovery alone is projected to grow from roughly $126 million in 2025 to nearly $640 million by 2035. The United Nations designated 2026 as the International Year of Quantum Science and Technology, a largely symbolic gesture, but one that reflects how far the conversation has shifted from theoretical physics seminars to national industrial policy. Even skeptics inside the field, the same physicists picking apart Microsoft's Majorana claims line by line, generally agree that the underlying hardware trajectory across the whole industry is real, even if individual claims deserve scrutiny. There's also a shadow side to this progress that's impossible to leave out of an honest account, because it explains why governments are pouring money into this technology with an urgency that goes well beyond scientific curiosity. The same quantum properties that let a processor simulate a molecule's structure could, in a sufficiently large and error-corrected machine, also be turned against the encryption that currently protects almost all global digital infrastructure, from banking systems to military communications. Current quantum computers are nowhere close to that scale yet. Breaking modern RSA, or elliptic curve encryption, would require millions of stable, error-corrected logical qubits, and today's most advanced systems are still measured in the hundreds of noisy physical qubits. But the roadmaps being published by IBM, Google, and China all point toward fault-tolerant machines with hundreds of logical qubits arriving before the end of this decade, and cryptographers don't wait for the threat to fully materialize before acting. That's why the National Institute of Standards and Technology has spent recent years finalizing new encryption standards specifically designed to resist both classical and quantum attacks, and why governments and financial institutions around the world are now in the early stages of migrating their most sensitive systems onto that new quantum-resistant foundation. It's a strange and rare moment in technology history. An entire global industry racing to defend against a machine that, by its own builder's admission, doesn't fully exist yet at the scale required to cause the damage everyone is preparing for. If you strip away the marketing language that tends to surround announcements like these, what actually happened in the past year is genuinely remarkable, and it doesn't need exaggeration to land. A machine built from superconducting circuits, cooled to a fraction of a degree above absolute zero, rid the hidden internal structure of a molecule in seconds, using a method no classical computer, however large its neural network, could replicate in any practical span of time. And unlike every headline-grabbing quantum claim before it, this one could be checked by other scientists and confirmed to be real. Separately, a hybrid quantum classical system pushed past the boundary where the most celebrated AI breakthrough in modern biology, AlphaFold, was structurally built to stop, opening a path toward understanding not just what a protein looks like, but how it actually behaves at the quantum level as it does its job inside a living cell. 3 major global powers, using 3 genuinely different physical approaches, are now independently reporting the same fundamental error correction milestone within roughly a year of each other, something that essentially never happens by coincidence in cutting-edge physics. None of this means the age of practical, everyday quantum computing has arrived. IBM's own timeline for full fault tolerance still runs to 2029, and Microsoft's topological approach remains genuinely contested inside the physics community as we speak. But the specific, narrow, and previously impossible claim in the title of this piece, that a quantum computer solves something artificial intelligence structurally could not, is no longer speculation. It happened, it was measured, and it was verified. The question the entire scientific world is now racing to answer isn't whether this technology works. It's how fast the rest of what it can do will arrive, and which of these labs in Santa Barbara, Hefei, Poughkeepsie, or somewhere in Redmond gets there first.